Welcome to the Air Code podcast, decoding artificial intelligence and robotics for all those who are interested in the field and want to learn more about it. For episode 2, we'll be talking about robots that can pick up objects. We'll touch on topics such as what it's like for a robot to pick up an object, why it can be so difficult to do if the robot doesn't know how to pick it up, and different ways that robotic grasping might be improved in the future, such as the use of artificial robotic skin. I am joined today by Dr. Juxi Leitner, a research fellow from the Australian Centre of Robotic Vision and the Amazon Robotics Challenge winner of 2017. Stay tuned to hear more about robots and how they can pick up an object. Today we have Dr. Juxi Leitner, who will be talking to us about robots that can pick up and grasp objects. Welcome, Juxi. How are you?
Hey, thanks. How are you?
I'm good, thank you. Juxi, I've invited you here today because I'm really interested in robotic grasping. So what are currently some robots out there that are picking up objects?
Well, I'm really interested in robotic grasping too, so thanks for the invite. There's a lot of robots out there that actually do something useful in the world right now. So there's a lot of industrial robots, and they're actually really good at picking up stuff from a specific location and place it in a different, but also very specified location. So for example, every car, every phone, lots of stuff that we actually buy is pre-built by robotic systems. But everything is pre-programmed and pre-scripted. So these robots are really good at picking up stuff that they know in locations that they know of. But the problem with that is actually that this doesn't really transfer a lot to settings that we want robots to work in. So usually you have to design the whole process around your robotic capabilities. So can the robot pick up this object, and where can it pick it up from? If you don't know exactly what you need to pick up, you have a perception problem. You need to understand what is coming to you, and you need to understand how to pick things up. For example, if I'm a human and I see a glass, I have an intuition or a learned model of how to pick up a glass in front of me, even if this is a glass that I've never seen before. For a robot, I need to pre-program everything right now. So if, for example, the glass changes, or if the part that I want to pick up changes, I have to write yet another program. So a lot of it comes back down to the robot's not very capable to adapt to change in the environment.
So what is the process if a robot wants to pick up an item? What are the steps that are currently being undertaken to get there?
So it depends on if you're talking about industrial robotic settings or research in grasping. So one of the main limitations of current industrial robotic settings is that they're very limited to this change that I mentioned. So the process is pretty much, I know where I need to go. I move my arm to where I need to go. I turn on my end effector. So end effector might be a suction cup or even a very simple gripper. I have some sort of basic feedback, usually from the vacuum flow, for example, of the suction cup that are actually attached to an object. And then move to another fixed position, and I release the suction cup again on this one. Problem with this process is that, for example, if there's nothing there at this position, or if a human is in the way, the robot doesn't actually understand that there's a human in the way. That's why we have all these curtains, like laser curtains, that actually stop robots when walk into the workspace, or even have them fenced off.
So how do we make it more safe for humans to be around robots that are able to pick up objects in this way?
That's a very good question. So there's lots of different ways of doing that. Here at the center, we're looking at how robotic vision can help solve this problem. So we're looking at how perception helps the robot to understand what the environment is all about. So is this actually the object that I want to pick up or not? You can, for example, use a camera that says, this is a red object, I want to pick red capsicum. So it's probably a good thing. This is a blue object, I have never seen blue capsicum, so I don't want to pick up this blue object. On the other hand, you can also build better robotic systems. So a lot of the robots that we built over the last decades that do all this manufacturing have sort of fallen in almost like a negative feedback cycle. You build more stiff robots, so robots that are very hard and very easy to control. Therefore, you can build more precise controllers that actually can solder, tiny microchips on things. But that means you actually build more stiff robots, because that means you're getting even more precision. That means you get better control and you get into this feedback loop. The problem with that is that as soon as you have a very stiff robot with a very precise controller, you cannot really react to things that are soft or a human around you. So people have started going the other direction and started looking at soft robotics, at, for example, printing skins that have a sort of a haptic feedback that provides the robot with some environmental feedback that is not vision. You have robots like a Baxter robot from Rethink Robotics that has steerless elastic actuators that actually limit the torque, so the force that's applied to the environment. So for example, if I realize that I'm going through something that has much more torque than I expect, for example, I hit the table instead of the object I want to pick up, I stop. Sounds very natural, but it's actually a very tricky thing for a robot. Even during my PhD, people were working on the a skin for iCup, the humanoid robot that I was working on, to actually feel when you run into the table, because the robot didn't have that capability. More and more Sears elastic actuated robots are actually in the world. I don't have numbers on that, but they are sort of at this cusp from turning from a purely research scientific endeavor into something that's commercially available.
What would be a good application for a robot to have soft skin and being able to identify different senses through that?
So soft skin is a very interesting concept. And there's two things that you want to think about. One is the deformability part of skin. If we run into something, our hands sort of slightly deform, so our skin forms around the object that we actually want to interact with. So that helps us on not breaking stuff. If it were, for example, a very stiff robot, think of like a branch on a tree. If it's very stiff and you actually try to interact with something, so you poke something, it starts to break off. If the branch is from a young tree, it sort of deforms still and it doesn't break off. So the same thing there, if you have something that's a skin-like deformable material, it helps you with interacting with the world. People have actually proposed that if you shift some of the computational effort from being a very stiff but very precise robot to something that's deformable, you actually have this shift of computational resources that goes directly into the morphological properties of the robot. In the end, there's proposals that is actually simpler to control than a very stiff robot. From the second point of view, skin also allows you usually to feel things. And that's the other very important feedback mechanism that we have. If, for example, I want to pick up something that's in my pocket, I just stick my hand in my pocket and I flip out my iPhone. I don't see the iPhone, I basically feel the phone. So if we could create a skin or skin-like material that actually allows us to cover a robotic hand, for example, with all these materials, we could feel our way around objects. For example, we could feel that, well, this is actually the handle of the object and I want to pick up the glass or the cup by the handle, not by just a random other part of it.
So how do we train robots to pick up objects and to be able to know what is the right object to pick up?
That's a very good question. And that's something that, for example, we work on, but there's a lot of research interest in the world right now in this one. Because we have this old sort of paradigm of programming the robot to pick up one specific object, this doesn't scale up. If we want to pick up every object that's in somebody's house, you cannot pre-program it. And especially if you would start to pre-program it, by the time you finish pre-programming it, there's a lot more objects and you end up in this problematic situation where you still can't pick up everything. One of the research avenues of the last couple of years, especially with the rise of deep learning for computer vision, is how can we use all these novel or improved techniques of using from a big data set into how can we make robots that actually pick up random objects that we place in front of them. There's different research avenues. Stuff that we, for example, have done at the ACRV here in Brisbane is how can I use reinforcement learning, which is a machine learning technique, to find good grasp points. If I have a lot of objects in front of me and I pick them repeatedly, kind of like a baby, I learn at some point that whenever I use the handle of the object, I don't burn myself, for example, if it's a hot cup. Or if I pick up a teddy bear at one of the legs, it keeps flopping around. So I do have some feedback from the world. And so we're trying to do something similar with reward signal, which will tell the robot, for example, that you had successfully grasped something. The other thing is how can I actually use that visual feedback? So even in the reward signal, you would have some feedback between what you perceive and what you do. So basically, we're trying to combine them and stick them together into something which we call vision and action, which basically creates a tight feedback loop around the perception system and the actuation system. There's a few problems with that. Just like, how do you benchmark that? What objects do you use? What gripper do you use? There's a problem with just choosing the right benchmarking method. But even apart from that, as a human, I don't have a success rate. I pick up something or I keep trying until I pick up something. Two issues that we are currently looking at is how can I generate grasp points without sampling? And how can I do this robust and adaptive enough that I can do that, for example, while reaching? So I continuously update my grasp points while I reach to pick up something. So coming back to the point of industrial robotics and manufacturing, we know how to do that, but we don't know how to scale up. As I mentioned before, if you have a lot of different objects in the world, how do you make sure that you still pick up all the stuff that's around you? And that's not just an academic, scientific problem. Amazon has the same problem. So Amazon started about 3 years ago with something they called the Amazon Picking Challenge, and it was mainly focused on picking in the first iteration.
So can you tell us a little bit about the winning robot? What was it that made it so different or such a standout compared to all the other teams that competed?
Yeah, so our robot we called Cartman, and that's because we actually used not a standard robotic arm, but a Cartesian manipulation system. So basically think of a claw system or a 3D printer, where you have 3 fixed axes and basically 3 motors that move along these axes. Plus, then we designed our custom end effector, which both used a suction and a pinch grasper. And they were 3D printed. And we ran through about 30 iterations of the design of that end effector in the couple of months that we had before the challenge. So we were very confident in the design of our end effector. The other standard is that it was actually quite cheap. It cost about 12,000 Australian dollars all in all to build that robot in just hardware parts, which is significantly different to some of the robot systems that we saw there. So apart from the hardware, I think the other crucial part is how do you interact between the different subsystems that your robotic system has. I think one of the crucial factors that helped us win was that actually from very early on in the process, we had a prototype, or at least a somewhat stand-in prototype full system that we tested. So we basically every week had a full system test, and we knew which part sort of kept us back most. And this is where we put our effort in. How well you integrated your systems, because again, if you had a mishap in the first part, it would lower the chance of getting more points in the second part.
You come from a long background of grasping and manipulation research. Will you share with us some of your favorites that you've done over the last few years?
That's really hard to pick. The Amazon Challenge win is clearly top there. It's just an amazing experience. Even if you would have not won, it was an amazing experience to take the team over to Japan, have the robots in parts on a plane, taken to Japan and assemble it on site. But I think also the team just had a lot of fun, so it was just a very, very great experience. Apart from that, I really enjoyed my work during my PhD on trying to get a humanoid robot to grasp things. It was a very complex hand. It was a very complex system. It was really still in the very early stages of development. So that's really a lot of interesting issues that arise with that. But here, over the last couple of years at the center, I think we have done some really cool work, both in how to use the deep reinforcement learning models to transfer from simulation to real world. So understand it's simple to simulate certain things. It's hard to simulate a lot of other things. But even so, if you run things in simulation and then transfer to real world, you have what is called a reality gap. You have this difference of your actual physics against your simulated physics, or your robot slightly different from what your simulated robot is. And so we came up with some cool ways of trying to adapt that with one of our PhD students. We also started working on what I briefly mentioned before, how to combine continuous visual servoing style techniques with grasping.
We see a lot of images online of robotic hands that look just like our hands. Yet when we look at the research and we see videos of robots picking in action, they always only tend to have what look like 2 fingers. Why does there seem to be such a big gap between being able to build something that looks like a human hand and only having robots currently that pick using 2 fingers, or as you said, using a suction grip?
That's a very good question. On one side, I think we are driven by building a human-like robotic system. As researchers in robotics, eventually we want to build something that can interact with all the objects that we as humans interact with. Turns out all the objects that you, for example, see in a kitchen or in an office around you, they're designed for your hand because you're using them. So there's the idea, or at least there's some drive in some of the robotics research that says if we want to interact with all the objects that humans interact with, we have to have something that at least is in somewhat form, shape, or capability similar to a human one. Secondly, I think why we don't see that in industry is, again, because of the process design. If you can design your process around a simple task, you don't need 5 digits. In fact, even as humans, sometimes there's been studies around that if you actually need all 5 digits. Turns out most of the time you only need 4 at max, or 3. For example, if you ever had a cast or a splint on one of your fingers, you realize that you're actually very adaptive and you don't necessarily need all your fingers. So there's a question, if you can design the process, you as an engineer obviously try to optimize this to use as least complex system as possible. Therefore, suction or 2-pinch grippers work in a lot of cases, and the 80-20 rule applies. It works in 80% of the cases, so we just used it in this 80% of the cases.
What do you think are some of the objects that are going to be the very last to be picked, the ones that can't be made by both graspers and suction cups that we currently have available?
I've been asked this before, and I'm not really sure. On one hand, I think there's nothing that's super tricky, and if you have the time and the resources, you can solve it by building one specific solution for that. Right? So if you have an industrial robotic setting and you need to pick up that very specific object, it doesn't matter if you spend 2 weeks implementing it, because then you can optimize it for a year, 10 years. however long you're using this object, right? So there's clearly a trade-off between a robot that's very specific for one item, even though it's a very tricky item, or a robot that is very capable in like 80% of the cases, but has problems with the other 20%. Generally, from the research that we're doing in research labs around the world around grasping, there's a few issues that we see and that we sort of all have to deal with as researchers. That's cloth and deformable materials. They tend to be very tricky, both to model but also to interact with. We have objects that are very hard to perceive, and that's basically based on limitations on both our camera system, but also, as you mentioned before, skin or deformable soft materials would be very good to have, but we don't have them yet. So anything that has a weird shape or is highly reflective, our cameras have issues with. So the haptics would be very interesting for these ones. So I don't think there's a silver bullet answer, as in like. But again, I think it depends on how you look at it. I think you can engineer solutions to everything, and we are very smart as human beings and researchers to engineer solutions. We build robotic systems that handle almost everything from nuclear waste to recycling to food produce, right? So there's a big range of stuff that we can program stuff to do, but we still lag behind systems that are general enough to handle multiple of those things at the same time, or reason about which way to handle certain things.
Looking into the future about picking different kinds of objects, how are we currently advancing with picking up transparent objects, things that don't have a clear color or even a boundary to them? Can you talk a little bit about picking up things such as a clear glass?
Yeah, so clearly that's a perception problem, like things that are highly reflective, that are clear, or that have basically the same color as the background. For example, during the Amazon challenge, we had to pick up a pair of scissors that were metal on the front, like highly reflective scissors, but red in the back, which was the same color as the tote that Amazon provides. So they're very, very hard to see for cameras. In fact, they're actually very hard to see for humans too, especially if they're in clutter and covered by the objects and materials. A different problem is glass and things that are see-through, especially in sort of the visual spectrum. There's been studies on how humans do that, and reflectiveness, things that seem to be reflecting on it, or lines that are changing. For example, if you look through water, you might see like there's a clear change in reflectivity of the water. So stuff like this usually helps us for reasoning around where the glass objects are. Turns out you can actually deep learn some of that too. So for example, during the challenge, we saw that see-through glass object on some of the backgrounds is actually very easy also for the deep learning system to detect. Learn similar features than what we do when we look at these scenes. I think there's a few issues on the perception side of these things. I think machine learning can help with some of that. The same with developing better sensors or fusing different sensors. While a glass might be really hard to see, it's actually still very easy to feel. So if I, for example, have some of those tactile skin-like sensors, I might be able to feel my way around a glass and see actually there's something in the world that I have a hard time seeing. The second thing might be to actually change your viewpoint. If you play peekaboo with like a baby, you move your way around and they move their way around to like place themselves so they can see more. Robots don't do that yet, but I think that's a very important thing as well, to keep moving in the world that you are and keep moving your camera in the world. I think it's a very important aspect of improving perception systems.
And what are some real-world examples where a picking robot could be helpful?
There is a lot of robots out there that already pick, and clearly you can improve them with better perception systems, better picking systems. Eventually, I think what we would like to have as roboticists is robots that can pick in a lot of places where humans are either scarce or where it's too dangerous for humans, or where it's just a very dull, repetitive task for a human. So that's why we don't have a lot of humans lifting like half-a-ton blocks for car manufacturing, because it's a health issue. It's also a very highly repetitive task. Some of the fine-grained welding is still done by humans because it's actually a much more interesting and a much more high return task to do. Tasks that I personally believe where we see more robots coming in and picking stuff is in conveyor belt systems where things are not always super structured. For example, because multiple things need to be picked, or high variance of objects needs to be picked. For example, fruit, vegetable. Although they're all sort of a carrot and they're all sort of orange, they're all slightly different, and they always will come in slightly different configurations. So you need a vision or perception system that helps you with that. Generally, there is a trend to have more SME manufacturing done by robotic systems. Instead of actually building the whole factory, now you can actually build robotic systems that are easy to reprogram or easily placed in these sort of settings with a human working next to them. Other places are where labor is scarce. For example, here in Queensland, we're looking at doing fruit picking, especially during the high demand season when it's super hot and super humid outside. Farmers are actually looking at other ways of harvesting fruit. Another option where I'll see it coming through very soon will be anything that is OHS, so health and safety related, where you need to pick from lots of bending over, like lots of tasks that you need to pick from the floor, or where you need to pick stuff from a very high up shelf. Plus stuff that is dangerous, for example, in recycling, if you need to stick your hand into like dirty things, you don't know what's in there. I think we have the capability now to translate some of our research into robotic systems that actually can help in these settings and make it actually a lot easier for humans to do jobs that are better for them and less health and safety risk.
Is there anything else that you would like to let our listeners know about grasping and picking?
The thing that fascinates me about this is when you start as an engineer looking at these things, you start looking at the problems and how to solve them. During my PhD and my postdoc, I actually realized how complex and amazingly built our hands are. So if you have time during the next meeting and it's super boring, just look at what people are doing with their hands, like picking up a pen, rotating it in their hands. These are all capabilities that require a lot of sensing, a lot of fine-grained control, and lots of our robotic systems cannot do that. So stare at people's hands.
Great, I'll be sure to give it a go next time. You've reached the end of another episode of the Air Code podcast. Got a question or topic for us to talk about? Connect with us on social media and let us know at the Air Code. Don't forget to subscribe to our podcast to stay up to date with content and news. See you in the next episode.